Okay, so and we will open the text. So, do you see it? Is it okay?
Yes.
Yes.
So today we will consider very important and practically oriented questions devoted to the methods of the switch capacitor circuit analysis. And we will introduce two main approaches. The first one is based on the presentation of the circuit using the so-called nodal equation of the charge and voltage relations, and the second approach will be based on a so-called Lakers model. And we will consider how to analyze the switch capacitor circuit on the Z domain. And of course, we will talk something about the practicum, and you will take one of the circuit to the home analysis, and we will see how it is. But what is important to understand, just now you have seen in front of you, so the text of the 7th chapter of the book. I think everybody has got it, and you can use, of course, this material. And we will consider it as a kind of presentation, but it doesn't matter, you have this text. So let's go. So the first approach is based on charge equation method, and it is the physical basics of the analysis. And it is important to understand the idea is to split the circuit, разделить схему, to split the circuit to two parts, на две части, to two parts. Each of them corresponds to the equivalent presentation of the switch capacitor circuit and the time domain on the current phase. So it means that if we are talking about two-phase control, as it was before, ну вот в том случае, если мы рассматриваем двухфазовое управление, как, собственно говоря, и было, so it means that on the first stage of the analysis, it is necessary to reproduce the circuit as an equivalent presentation of it. And one very important proposal, and we can say the kind of idealization. It is necessary to keep in mind that on this approach, each switch is considered as the ideal element, ideal switch. It means that we have only two conditions for each of them, close or open, and the internal resistance of the switch is also ideal. Say other words, it is equal to 0 or it is infinite. Do you understand this proposal? In Russian, предполагаем, что ключи идеализированы, то есть два состояния имеют. В этом смысле они как бы безинерционные, то есть либо открыт, либо закрыт, и внутреннее сопротивление идеализировано. То есть в закрытом состоянии, естественно, 0, в открытом состоянии, наоборот, бесконечно. Понятно, да? Вот это, собственно, исходная модель. So, well, and from the physical point of view, it is important to understand that if we are talking about the classical approach for the circuit analysis, that the Kirchhoff law is the basics of this approach. Yeah, you know about it. Законы Кирхоффа — это основа, собственно, анализа любой схемы. And the Kirchhoff's law are based on we can on the law of conservation of energy, на основе закона сохранения энергии. And there is one very serious difference. If we are talking about a discrete time circuit, that another approach should be used. In our case, it is the law of conservation of charge. В данном случае, вот когда мы говорим про схему на переключаемых конденсаторах, речь идет о законе сохранения заряда, а не энергии. Обратили внимание, вот это вот момент принципиально важный. Так? Say other words, this approach is valid. We are talking about the rechargeable capacitors, and the question is how the charge will be distributed among the circuit capacitor, which are included into the structure of the circuit. То есть, другими словами, речь идет о том, что необходимо получить некий инструмент, который бы позволил вот понять распределение зарядов на конденсаторах, вот в которых, собственно, происходит вот это вот переключение. Понимаете? Вот, собственно, основная проблема. So, and coming back to the physical principle of the work of switch capacitor circuit, we can say that it is possible to formulate the law, a kind of theorem, of course, it is a kind of theorem, and it is the rule how to formulate the charge injection of each node of the circuit. You can see it is here, well, just now I will demonstrate it to you, this one. Yeah. So, and it is possible to say that the charge injection to the eth node at the gth phase delta Q is equal to charge stored at capacitor connected to this node at this phase, except for the charge that was stored on the same capacitor. What is important? On the same capacitor during the previous phase. So, and if we are talking about the standard approach, which is based on two-phase control, если мы говорим о стандартном ситуации, когда используется двухфазовое управление, вот как в тех случаях, как мы с вами уже рассуждали, так сказать. So it means that it will be possible to formulate this law for the each phase. For the each phase. So it means that the number of equations corresponds to the circuit will be equal to the number of nodes, but twice, because we should prepare these equations for the each phase. То есть, другими словами, количество уравнений будет соответствовать количеству узлов, но только при этом удваивается по количеству фаз. So, let's try to understand how it is. So, look into this formula. Look into this formula. What we have? First of all, the upper index in our case G, correspond into the number of phase. It is number of phase. Look. So the lower index I, corresponds to the number of node. And so on the bracket we have the time slot, as usual. T, the capital T corresponds to the period of the clock frequency, and the tau is the time of this, then in our case of the G's phase. So it means that, so look, the changing the left side, the changing of the charge on the eth node corresponds to the charge that was stored on the capacitors which are connected on this phase to this node. So look, and the number of these capacitors corresponds to this sum, and it is necessary to delete from this sum the charge that it was on the same capacitors but one clock before. You see, say other words, on the previous phase. So it means that here on the of the number of phase we have -1. It corresponds to the previous one, and of course we have the time delay for the time of the phase period. So what we have? So let's try to understand how we can do it using the more general circuit. So you can see here on the figure 7.1, you can see here on the 7.1 a so-called generalized switch capacitor circuit. It is one capacitor C1 and 4 switches which are connected to the upper and to the bottom plate of the capacitor. The bottom plate will be noted as the bold line, жирненькой линией вот такой. Нижнюю обкладку конденсатора будем выделять жирненькой линией, as the bold line. The question is, it is necessary to keep in mind the polarity of the voltage on the capacitor. And we will say that the positive polarity of the voltage on the capacitor is from the upper to the bottom plates. То есть будем считать, что за положительное падение напряжения на конденсаторе берем направление от верхней к нижней обкладке. Вот так. Поэтому обкладки надо аккуратно обозначать, господа. Вот это вот важно. So, okay. So, and also coming back to this strategy of our analysis, it is necessary on the first stage to prepare the equivalent presentation of the circuit on the phase which are considered. Say other words, on the first number 1 and on the phase number 2. So let's try to do it. So look, the phase number 1, it means that the left switch is closed, the right switch is closed, and the second pair of the switches are opened because they should be controlled on the second phase. Say other words, it is opened too, and this closed and this closed too. So it means that here on the next picture we can see the equivalent presentation of the circuit. So look, it means that on the first phase the capacitor is included between two nodes, number 1 and number 2 in the first phase, and between node number 3 and node number 4 on the first phase there is nothing. Ничего нет, there is nothing. And vice versa, и наоборот, and vice versa. On the second phase, the first switch is open, the second switch is open, and the third switch is closed, and the fourth switch is closed too. So it means that on the second phase, we have the structure like here. Like here, you see. There is nothing capacitor between the node number 1 and the node number 2, but the capacitor is included between node number 3 and node number 4. So what we have, this is equivalent presentation of the circuit on the time domain, by the way. So, and just now it is necessary to use this rule for the presentation of the charge voltage equations to analyze the circuit. So first of all, look at here. We can talk about the node number 1 on the first phase, and the charge injection on this time will be equal to the charge that which is just on this time on the capacitor. So it means that we can use this notation. It is Q on the capacitor 1 on the first phase on the time which is equal to the time slot. And it is necessary to delete, so look, it is necessary to delete the charge which was on the same capacitor 1 clock before. So, and it means that it is necessary to do the minus here, to use the minus sign here, and use the second phase capacitor number 1. Of course, the time also will be changed because it is corresponds to the second phase. It was before a half of clock. So the second node number 2 here, number 2, this one corresponds to the same charge injection but with the opposite sign. The idea is, so look, we are talking about the sign of the injection from the left to the right, say from the external node to the internal, to this direction, and from this point of view, the same situation is for the second node. It means that the charge injection will be like that. Say other words, it is possible to understand that the charge injection from the left side and from the right side will be opposite to each other. in Russian. Ну, собственно говоря, принимается, как и в любом трехполюснике, да, направление протекания снаружи вовнутрь. И поэтому тогда получается так, что вот мы смотрим, собственно, на изменение заряда со стороны первого узла. Вот оно будет вот в эту сторону, со стороны второго узла в эту сторону. Ну, и таким образом, как мы видим, они противоположно направлены, видите? Поэтому, следовательно, для этого простейшего случая, it is possible to conclude that we have the same charge injection, but with the opposite sign here. So the next node number 3 and the node number 4. No, so well, it is possible to say that we do not have anything here. So look, there is nothing. So it means that the charge injection will be equal to 0. And we have the third and the fourth equation with the number with the right side, which is equal to 0. So that's all. That's all. Say other words. Say other words. What we have? We have 4 equations, 4 formulas for the first phase of the switch capacitor circuit. In general, as you can see, it is twice because we have 4 nodes, and just now it is necessary to organize the same procedure for the second phase. Look what we have here. Second phase. On the second phase, there is nothing between the node number 1 and the node number 2, so it means that the charge injection will be equal to 0, and we have it. So look. And we have 0 here, we have 0 here, yeah. So, and the next equation corresponds to the node number 3 for this one. For this one on the second phase, So it means that we have the charge on this on the same capacitor. It is here, and with the exception of the charge on the same capacitor before, say, on the first phase. So it means that we have like here. And taking into account that on the opposite node number 4 we have the same situation but with the opposite sign, it is possible to conclude that it will be for the fourth equation we have the same but with the sign minus here. So more or less it is understandable. So I think maybe you have some questions, please ask. Any questions?
Все понятно.
Yeah, let's go further. The next stage. It is necessary to introduce into the formulas the voltage drop between the capacitor plates, upper and bottom. Необходимо ввести падение напряжения теперь на конденсаторе, да, между верхней и нижней обкладкой. So it is necessary because it is possible to rewrite the formulas for the charge of the capacitor on this form. So look, the right side of this equation corresponds to the charge of the capacitor, which is presented using the voltage drop on the capacitor. You see? Voltage drop on the падение напряжения на конденсаторе. So once again, coming back to our notification, we said that the positive voltage drop will be from the side of the upper plate to the side of the bottom plate. С верхней на нижнюю обкладки будем считать, что это есть положительное падение напряжения, да? So it means that it is possible to conclude here that we have the following equation for the first formula. I mean this one. So the voltage drop on the capacitor is equal to this difference, this one. And before, on the previous phase, it is important to remind you that the capacitor was before the node number 3 and the node number 4. So it means that here, on the second part of this formula, the indexes here and here will be changed, and if on the first position, on the first term, для первого слагаемого, on the first term we have the numbering as voltage 1 and voltage 2, say other words, it is the voltage on the first node and on the second node, that for the second bracket here we have voltage number 3 and voltage number 4. Say other words, it is the second pair of the nodes. Это вторая пара узлов, видите? So, well, and the second formula will not be changed. Of course, it will be equal to the first one with the minus sign here. С минусом, ну, собственно, знак меняется. Остальное все так же. So, well, the third and the fourth equation are equal to 0. And here on the second part also we have the same situation. And it will be necessary to change the voltage drop on the next one. So you see what we have here. On the second phase, the capacitor on the second phase is included between the node number 3 and node number 4. То есть во второй фазе конденсатор между третьим и четвертым узлами включен. So say other words, the voltage drop on the capacitor will be equal to this difference on the square bracket. Тут будет равно разности в квадратных скобках вот здесь. So, and of course it is necessary to delete from this charge the charge that it was before, 1 clock before. То есть убрать, собственно, заряд, который был на конденсаторе один, ну или точнее полпериода, на один такт как бы, да, один такт назад. Вот, so it means that we have this equation. The last one will be exactly the same as previous, but with the sign minus. So generally speaking, that's all. And some notation concerning the shift in time. So look at here. Generally speaking, if we are talking about the properties of the Z transform, it is necessary to keep in mind some specific. It is not possible to use the time delay which is not equal to the digits. Ну, собственно говоря, нельзя отличаются от целого числа, видите? It is necessary to keep in mind this situation because here we have a kind of time delay for the half of time period. Sorry. Sorry, are you listening me? Is it okay?
Yeah.
So well, and so it is necessary to think about this situation, and we will consider this. Also, how to say this? This time distribution, I would like to say, as a kind of specific time delay for the family of the equations, not for the Z transform. То есть, другими словами, будем рассматривать вот, ну, это кажущийся такой как бы парадокс, вот со сдвигом вот так вот на пол индекса, как своего рода задержку на полтакта для всего семейства уравнений, которые рассматриваются, так, чтобы не было противоречий со свойствами Z преобразования. То есть, вот это вот будем иметь в виду. Потому что по-нормальному, конечно, коль скоро мы как бы здесь работаем с индексами, но индекс не может быть дробным, понимаете? То есть вот такой момент, в общем, важный есть, поэтому на это обращаем на всякий случай внимание и будем трактовать это просто как задержку на полтакта, а не изменение порядка индексирования. Хорошо? Значит, вот, господа, вот это вот, пожалуйста, keep in mind, что называется. Ну, so, okay. Just now, it is possible to use the Z transform for all of these equations, and it is possible to use it on accordance with the properties that we have discussed before. And coming back to these properties, I would like to remind you about the time delay theorem. So, and exactly using this notation, we can see that it will be equal to this series, to this family of equations, and we have 1, 2, 3, 4, 1, 2, 3, 4, say 8 8 equations corresponds to our circuit. I would like to remind you once again that the number of nodes is equal to 4, but each node will have their own statement, свое состояние, in each phase. And if we are talking about the two-phase control, it means that the number of equations will be equal 4 multiplied for 2, so say 8. То есть, другими словами, по количеству фаз управления. То есть, учитывая, что у нас 4 узла, следовательно, с двумя фазами, получаем всего 8 уравнений. Вот мы здесь 8 уравнений имеем. Okay. Okay, what we have? And just now it is possible to implement the matrix approach to the generalization of the such type results. Значит, для обобщения результатов используем матричный вид. So it means that the equations will be equal to this presentation. Значит, следовательно, уравнение можно свести вот к такому представлению, as you can see here. And as the last stage, as the last step, we can say it is possible to delete from this matrix the 0 column and lines. So in other words, we have a number of 0 columns and we have a number of 0 lines, and it is possible to delete it from the matrix. After this operation, we will have the result. And generally speaking, that's all. Generally speaking, that's all. And as you can see, it is possible to generalize this approach if we are talking about the number of connected capacitors. Of course, for each node, it will be necessary to formulate the same formulas, and after all, to represent it in the matrix form. Соответственно, не один конденсатор, а соответствующую картину конденсаторов, соответственно, схему, да, то после этого каждый узел будет соответствовать какому-то уравнению, после чего обобщаем все это дело в таком виде. Any questions, please? Yeah, I'm listening.
I think it's clear. Thank you.
That's good. That's good. So, and the Lecture approach. The idea is, is it possible to present the switch capacitor elements using a kind of equivalent element on the Z domain? And in general, it was possible. And firstly, Professor Kenneth Lecture from the US was the first who proposed this approach. And the idea was, so look, if we are talking about the general form of the charge voltage equations, когда мы говорим вот об общем виде, да, вот этих вот уравнений, которые получили название заряд напряжения, да, в базисе заряд напряжения. So it means that we have the general formula like that. And it is possible to take into account that if we will normalize the left side and the right side of this equation using the time period of the clock, that we have the following ratio. So look, and it means that in general case, the right side of the equations corresponds to the current. It means that on the left side here, we have a kind of Y matrix, say a kind of elements which corresponds on the time domain to the conductance of the capacitors and another elements. And it means that it is possible to introduce the specific Z domain elements for the presentation of these equivalent circuit and of this equivalent component. То есть, другими словами, господа, вот посмотрите, здесь по размерности видно, что если занормировать левую и правую часть вот уравнений заряд напряжения на период тактовой частоты, то, следовательно, вот получим вот такое вот преобразование. И тогда видно, что, в принципе, вот первая часть, первый сомножитель вот этого выражения будет соответствовать проводимостям. Что, собственно говоря, и положено в основу этого дела. То есть, другими словами, следовательно, выходим на базис узловых напряжений. Видите? Потенциалов. То есть, собственно говоря, вот в эту сторону идет. So, well, and the Lecция model corresponds to two types of elements. You can see these elements, we can say components, more precisely components, более аккуратно говорить компоненты, поскольку все-таки это некий гипотетический элемент. And these elements are the first one, this one, and the second one. You see that the first element, this, corresponds to the resistive element, and the second corresponds to the storage element, элемент задержки, to the storage element, and the time delay corresponds to the half of clock period, you see, and this is exactly the time of the phase. То есть в точности соответствует вот при том варианте управления, который мы рассматриваем, половинки. Вот, собственно, это как раз та самая 1/2, вот, которая возникает там, когда из индекса k вычитается половиночкой, да? So, and as you can see here, the first element is an ordinary conductance. Yeah, and the second admittance corresponds to the storage element. And usually it is called, as you can see here, staristor. So look, it is called a staristor. And of course we will use the same notation for them. So, and the symbols for this element is here. The first resistive element is like that, and the storage element, staristor, is like that. It is important that the sign can be plus and minus for both of them. То есть знаки могут быть и плюс, и минусы для того и для другого. It depends on the phase consideration, and it is necessary to keep in mind the time delay. Необходимо принимать во внимание задержку на вот эти полтакта, ну и, следовательно, вот как раз появляется вот этот плюс-минус. So it means that coming back to the general equation like here, it is possible to rewrite it using this approach. So look, we can consider the charge voltage equations in accordance with this notation, в соответствии с вот этим обозначением, where Y corresponds to the conductance of each element. And it is possible to say that the Y elements will be considered as the resistive element or as a storistor. Well, this is an idea. It gives us the possibility to use the main approach that we know well from the results for the classical analog circuit. And here I would like to remind you once again some properties of the Y matrix. You can see it here. And first of all, the diagonal elements here, this one, as you can see, it is equal to the sum of all conductances which is connected to the node number I. And of diagonal element is equal to the negative of the sum of all conductances between the node I and J. So it is important that the Y matrix of the passive, continuous time and discrete time circuits are symmetric, and the X of symmetry is the diagonal. Say, in other words, the upper triangular is equal to the lower triangular. Значит, вспоминаем, господа, да, на всякий случай, мы об этом уже в этом семестре говорили, но тем не менее, значит, матрица симметрична относительно главной диагонали, верхние и нижние треугольники равны для пассивной схемы, как аналогового типа, так вот и дискретного. So, and it is important that we have the last rule, which is the last condition, or we can say properties of the Y matrix, about the summation of the elements. You can see the sum of elements of the Gth column is equal to the sum of element conductances, which are included between the node number G and the ground node. You remember about this, and from the practical point of view, it is the rule for the verification or validation of the Y matrix when we are talking about the practical examples. So, just now, no, yeah, of course, you will see some details on the text, but it is some rule how to prepare the equivalent presentation of the circuit. But you see, the moment is that the general approach is the same as before. Once again, firstly, it is necessary to prepare the presentation of the circuit on the time domain on the first phase and on the second phase. То есть сначала здесь, господа, точно такое же. Сначала рисуем эквивалентное представление схемы в первой и во второй фазе. Once again, of course, we will suppose that the switches are ideal. Предполагаем ключи, опять же, идеальными. Yeah? Say other words, it is only on two conditions, close or open. And say other words, the internal resistive losses are equal to 0 or infinite. То есть внутреннее сопротивление ключей, естественно, либо нулевое, либо бесконечно, да? So it means that after all, it is possible to formulate the Lecture model on the Z domain. So look, the rule is as follows. First of all, coming back to the general structure of the circuit, I mean the figure 7.1 here. So in general, we have 8 nodes, 1, 2, 3, 4, 1, 2, 3, 4. 8 nodes in a whole. То есть в целом будет 8 узлов. Не 4 узла, а 8, поскольку две фазы. This is the first. So on the first phase, the capacitor is connected between this pair of nodes. On the second, it is connected between this pair of nodes. What we have, so look, on the Lecture presentation, значит, на модели Lecture, что мы имеем, посмотрите. So the resistive element is included between the first pair of the nodes and between the second pair of the nodes, here and here. And after that, it is necessary to include into the circuit storistor element. So, and it will be connected the upper and bottom plates of the capacitor. And if we are talking about the opposite plates, the sign of the storistor will be minus. If we are talking about the same plates of the capacitor, the sign of the storistor will be plus. So look, keep in mind that we have the capacitor here. On the physical level, we have the capacitor here, we have the capacitor here. And from the left side, here and here, there is the upper plates. So look into the figure 7.1. On the left side, we have the upper plates. So it means that here we have the upper plates and here. It means that storistor, which is situated between these two nodes, will be with the sign plus. If we are talking the storistor, which is included between the upper plate from the first phase to the bottom plate on the second phase, which is included here on the diagonal of the figure, like here. So it means that each is the sign of it will be minus. So it means that we have exactly, just a second. Exactly this situation. So look, this storistor is included between the upper plate of the first phase and between the bottom plate of the second phase. It means that the sign is minus. You see, it is minus. And on the left side here, we have the storistor, which is located between the upper plate on the first phase and the same upper plate on the second phase. It means that the sign is equal to plus. The sign is equal to plus. The same situation from the point of view of the bottom plate. So look, on the right side we have the bottom plate here and we have the bottom plate here. It means that the storistor which is included between these nodes will be with the sign plus, and with the opposite sign minus. Look at here, minus here, because it is located between the bottom plate on the first phase and the upper plate on the second phase. Well, this is an idea. This is an idea. So, and what is just now important? The rule how we can formulate the Y matrix in accordance with this circuit is totally known for us. And it means that just now it is possible to formulate this Y matrix very fast. So look, for example, for the first node, I mean this element. Element Y11, the first one, this, sorry, yeah, what this one. So what we have, 3 conductances are connected to the first node, to this one. Conductor C1, this one, conductor C1 with the time delay, this one, and the third, this one, with the sign minus. We have 3 terms, имеем 3 слагаемых, C1 with the time delay, and the C1 with the time delay with sign minus. So it's okay, it's okay. So for the second node, this one, we have the same situation. Also we have 3 conductances, this one, and this one. And also it is the summation here. C1 with the time delay, and minus C1 with the time delay. Of course, exactly the same situation with the node number 3 on the second phase and the node number 4 on the second phase. So the upper and bottom triangles are equal, you can see here, and so as an example we can talk about the second element, this one. It corresponds to the conductance which is located between the node number 1 on the first phase and the node number 2 on the first phase. It is C1, this conductance, and we can introduce it into the matrix with the sign minus. You can see it with the sign minus. So if we are talking about the next element, this one, it is situated between the node number 1 on the first phase and the node number 3 on the second phase. Say other words, it is this conductance, and we have it with the sign minus. And the last, this one, this is the conductance which is located between this node and this node. So it means that we have these conductances with the opposite sign. It is minus here, and the opposite sign means that it will be plus. No, so that's all, and another elements will be introduced using the same approach. One question personally to Victoria. Вик, как вот у вас проблемы были на семинаре тогда, когда мы смотрели, там что-то забыли уже. Сейчас вы вспомнили? Посмотрите аккуратненько на это. Алло.
Да, извините, пожалуйста, у меня что-то прервалось, поэтому я последнее время не слышала. Вот, но вообще я разбиралась, да, с этим. Вроде бы как более-менее понятно стало, вспомнила то, что было.
Смотрите, вот, собственно говоря, то, что мы там вспоминали, естественно, вспоминали для того, чтобы сейчас вот с этим свободно, в общем, общаться. Так что вот как раз это напоминалка такая, в общем, имейте в виду. Вот вокруг этого, следовательно, дальше там будем смотреть всякие задачи там и все прочее. Окей, ну, let's go. let's go.
Alexander Slanic,
Да.
this method, this Lakers method, so we get the same matrix as with the charge method.
Да. Ну, конечно.
The Laker method, is it the more generalized form, or is it just completely different approach which yields the same result?
Generalization, of course, because from the physical point of view, the basics are the same. It is the charge conversation law. В основе, конечно, закон сохранения заряда, и он и там, поэтому это только форма представления. Да, одно вытекает из другого, конечно. Okay?
То есть нам просто для понимания первый метод
Да,
был
конечно.
полезен, так мы, в принципе, пользуемся вторым, он с виду удобнее.
Да, естественно, совершенно верно. Потому что формально, в общем, можно обойтись без введения вот этих эквивалентных компонентов и, естественно, делать, ну, собственно, как вот по классике, да. Но понятно, что вот так это проще просто. То же самое, в общем, по идее, для обычной классической схемы, в общем-то, там точно такая же история. Можно же рассматривать это все как систему уравнений Киргофа и, в общем, в частотной области ничего не рисовать. So, let's go. One moment concerning your exercises. So look into this circuit. This is the next one. This is the next general structure, and you can see that it is also capacitor C1 with 4 switches, but of course with another configurations. Look, the difference is that on the second phase, the polarity of the capacitor will be opposite with the comparison with the figure 7.1. По сравнению вот с предыдущим рисунком, вот 7.1, да, посмотрите, здесь полярность меняется. It is interesting to say that firstly, this circuit was introduced by Professor Maxwell. As I remember, so in 1871 or 73, something like that. And you see, after 100 years, the circuit was practically used, if we are talking about the switch capacitor. But on that time, more than 100 years ago, Professor Maxwell demonstrated that these components is a kind of equivalence of the resistor. Say other words, it is possible to say that he was one of the pioneer who was introduced the discrete time circuit, you see. But anyway, of course, he is very known gentleman. So, okay. And it is possible to use the same approach. It is the second example. And you see that there is a big difference because just now the polarity will be changed, and you can see that the diagonal elements, this one and this one, will have the sign plus. You see? The sign plus here and the sign plus here. But the left and the right sides components will have the sign minus. Minus here and minus here. So it means that the Y matrix will be changed in accordance with this changing of the circuit, and we will have the results like that. For your exercise at home, use this second circuit and to analyze it using the charge voltage equations. Say other words, the general approach that we have used before on the previous paragraph, you see, and for your training it will be good, because you know the result, the matrix is here, and of course it is prepared using the Laker model approach, but it is possible to demonstrate that the charge voltage equation will have the same results, and of course you can compare it. So please do it. Значит, господа, дома посмотрите вторую схему, да, вот эту вот методом заряда, да. Значит, для тренировки обязательно сделайте, ответ есть, поэтому, в общем, легко сравнить. So, and just now it is possible to consider the kind of generalization of this approach, and on this table, you see a number of Laker model of the switch capacitor for any possible situation, practical situation. And it is important to just a second to to concentrate your attention here. Yeah. Yeah. On the last positions. I mean this one. So look, there is one serious difference between the previous results and of this one. The question is that it is possible to demonstrate that on these cases, when on the second phase plates are not connected to internal node, to internal nodes, the time delay will be equal to -1 instead of a half of 1, you see? Вместо половинки здесь целое время задержки появляется, на целый такт. And the reason is that on the second phase, you can see that the plates are not connected to internal nodes. Say other words, there is no any recharge operation for this capacitor. То есть, другими словами, получается так, что во второй фазе конденсатор не перезаряжается, и тогда, следовательно, на нем остается тот же заряд, понимаете? И тогда, следовательно, вот здесь задержка становится не на полтактика, как вот 1/2, да, отображает, а на целый такт, минус единичка. The same situation, of course, if we are talking about the particular case when the second node is grounded. Ну, то же самое, естественно, в частном случае, когда один из узлов заземлен. So it means that we have the equivalent presentation of the Laker molded like here, and once again, time delay is equal to -1. And I would like to ask you to demonstrate it also. Please try to explain what we have here, because it is possible to calculate these elements and to demonstrate that exactly the time delay will be equal to -1. Так, господа, теперь ситуация следующая. Вообще, вот так вот, если бы мы в классе занимались, вот сейчас бы, конечно, вы вот эти два примера разбирали бы самостоятельно. То есть, в принципе, вот у нас остается как раз где-то там полчасика времени для того, чтобы вот вы два вот таких вот примера, минут по 15, вот так посмотрели, ну и получили результаты соответствующие. Сравнили там, обсудили ошибки там и прочее. Но понятно, что сейчас в такой ситуации это сложнее сделать, поэтому все-таки вы дома, естественно, сейчас посмотрите, как и что. Ну и если вот вопросы возникают, то в следующий раз с этого обязательно начнем. Okay, so as the summary for today, it is important to do some exercises. The exercise 1 is the analysis of this circuit. The analysis of this circuit on the time domain and using the charge equations approach. This is figure 7.4, and analysis of the structure from the table. Where is it? Yeah, this one. You can say you can take the simple thing. So, for example, this one, the grounded case. The grounded case. Let's try to realize it. How it will be. I can say you that it is possible to consider the structure like that, and it is necessary to, sorry, I think this one, yeah, the structure, and it is possible to say that there is no anything connected to this node on the second phase, and it means that it is possible to recalculate from the equivalent point of view with this part of the circuit, and let's try to do it. So, and more or less it is all for today. The next time we will start from the consideration of the results of your home analysis, and we will consider the active circuits analysis. So first of all, integrators. Yeah. So any questions? Just now we will open the screen. Any questions? And of course you can ask about the student work also. I mean your homework. Oh, let's go. I'm listening.
Okay, excuse me. I have a question about the coursework.
Yes, please.
Okay, so excuse me. I'm just gonna share my screen with you.
Yes, please. If it is possible, yeah, you can see.
Yes.
You can do it.
Do you see the screen?
Yes,
So
yes.
I just want to show you two things. So I made two realizations of these circuits. This is the one without the inverter. And as I run the analysis, the results are not correct at all, even though it's the same values. But now I'm gonna show you the second circuit that is with the inverters. Sorry, here at this, and I get such results. It means it looks more or less correct because my limit is 1.25. So do you say, please, can I use this one with the inverters, because I just removed this and it doesn't work. I don't know why.
Yes, of course. The reason is very simple. The question is that this is the voltage buffer. This is the voltage buffer. I mean the first. I mean the
Yes.
first block. This is the voltage buffer. It means that the input, you see, input impedance of the circuit is very, very large, very high. The input impedance is very high. But if we are talking about the inverter, the second, if we are
Yes.
talking about the second block, that the input impedance corresponds to the first resistor. You see the difference? For this block, for the first component, the input impedance is equal to mega ohms. But for the second component, it corresponds to, I didn't see it, but I think it is kilo ohms.
Excuse me, which resistor do you want? This one or this one?
Yes, of course, this one. Of course, this. Yeah.
This is 100,000.
100,000.
It's just for the gains. These are because I want gain 1.
Yeah, of course, the standard here 1 kilo ohm and 1 kilo ohm here.
Yes, I can change it to 1 kilo ohm. It's just for the gain. I think I can change it to 1 kilo ohm without.
Yes, of course. Once again, so look. So the question is that we need a kind of voltage buffer between the first resonator and the second resonator. It means that the input impedance of this voltage buffer should be very, very high. And there is the big difference with the input impedance for the first block and for the second block. The input impedance of the first block is very high, but the input impedance for the second block is very low. And this is the reason of your difference of two circuits. On this case.
Yes, so we need impedance matching.
Yes,
Matching.
Yeah, of course. Right. Yeah.
Okay, so thank you. This is all my questions. So I think I should leave it as it is. It's last time I tried fifth order, it didn't work. Now I tried sixth order, and it's correct.
Yeah. There is one very simple. There is one very simple recommendation. It is necessary to delete both of these components, the buffer and the inverter, and to use non-inverting amplifier here. Non-inverting amplifier. Do you know this circuit?
It's like the same thing, but the plus is here.
Right, of course, yes, right. And it will be possible to use one block instead of two.
Okay, so if I just change the same circuit and if it will be plus, it will be correct results with the same values.
Or both of them. It is possible to delete from the circuit buffer and inverter and to use only one non-inverting amplifier. Understand?
Yes, I understand. Now I will just show you. So something similar to this, but the plus should be here. Now I remove it. I only have.
You can see this. You can see this amplifier in any handbooks. In any handbooks.
Yes, like this. I know. Okay, so my last question. Thank you. I understand now. For this circuit, it works. Should I include in the report just to see as a variant? This one?
No, it depends on you. It depends on you.
Okay, so I will put it just for explanation. Extra. Okay, thank you very much.
Yeah. So the next students, the next question, please.
Я хотела бы уточнить насчет того, как получить дальше задание. Вам прислать на почту результаты или можно будет...
Да. Тогда готовьте краткий отчет, ну, в общем, так сказать, так, чтобы понятно было, что сделано. Там, так сказать, текст может быть минимум, но во всяком случае графики все должны быть приведены точно. Вот то, что вы сделали, естественно, показывайте. То есть вы должны сейчас продемонстрировать вот некую законченную часть по ФНЧ и дальше уже двигаться там по полусветам.
Все понятно. Спасибо.
Ну, на почту присылайте, я буду смотреть.
Можно еще спросить, вот вы говорили, можно подойти вроде в университет,
Ну да.
или это уже не особо актуально?
Так нет, зависит.
Надо со старостами договориться.
Да, тут просто зависит от того, что вы хотели показывать. Поэтому, если можно обойтись и переговорить, естественно, по почте, то хочу приходить, тогда можно и по почте. А если там действительно что-то серьезное, ну тогда, конечно, надо договариваться о встрече. Так у вас какой вопрос?
Не-не, мне просто показать. Я тут, я в общежитии живу. Тут
Давайте то, что Вика сейчас спрашивала, то есть готовьте сначала вот в таком электронном виде, присылайте, а потом там будем разбираться. Если надо будет, ну, естественно, подойдете. Если не надо, тогда что подходить?
Хорошо, спасибо.
Так, ну, something else?